I want to know. There's no way that she just is here. Well, because that whole, they live on the body and they put it on like the song that she made. It was the main tree.
How y'all doing? So I did put up on D2L a new section in the quizzes. It says makeup points quiz. Did y'all see that? So that makeup points quiz is up. Well, the one for test 1 is up. I'll get the one for test 2 up soon. If you want to go ahead and do that, you can. And I will at some point in the near future go through and fix up your grades for test 1.
When will that be due?
I don't know if I'm even really gonna put a due date on it. Just between now and the end of the semester, if you want points added to test 1, get to it. And at some point, I'll calculate, once a lot of people have done it, I'll go through and recalculate grades for test 1. So I don't really think there'll be a due date on these. Okay, so I put up here the things we've gone over so far for test 3. Test 3 everything kind of fits in its own neat category. In test 1 and test 2, all the information kind of overlaps. So just to put that in your head, these do kind of fit in neat little categories. So we're going to start a new thing today called specific heat. When we canceled lab suddenly that 1 week, we eliminated a lab on specific heat, but we did actually have a lab designed for this, but we'll end up doing it this semester. Actually, Sophie ended up doing it for a separate project, but now, so here we are, we're going to talk about specific heat. And let me start by giving a general description. This is degree C. This is just a temperature line. Let's just say this is temperature. So this is 0 degrees C. This is 50 degrees C, 100 degrees C. 105, 110 would be up here, and negative degrees C would be down here. The Celsius scale is designed actually with water in mind. You take whatever temperature it is, the water melts, and you tag that, and then you heat up the water, heat it up until it turns into steam, and that temperature that turns into steam, you put 100, and then you put 100 tick marks in between here, and what you've just done is create the Celsius scale. Celsius is based on 0 to 100 scale. This is where ice melts, and this is where water boils. You with me? So this is a temperature scale, Celsius. And I'll write, well, I won't write it. Just realize down here, I'll write that. Let's see. Here, water is ice. And here, it's ice that is solid water. Here, this is, I think, where we just say water, but this is liquid. And up above here, we have what we typically call steam, which is gas. Okay, just notice this wording-wise. This point, we always say melting point, boiling point, but we mean a temperature. The point we're talking about is on the temperature scale. Going from down here across this line up here, if you're heating it up, you would call that melting, right? You could also call it liquefaction. All right, but let's say you were liquid water and you cooled down and you froze going this way across this line. We call that freezing. I guess you could also call it solidification. But the word we typically use for that is fusion. Things fusing together. That's the fancy term. Okay, and again, I'll do the same thing up here. Here, your water, and when you're heating up as water and you cross this line going this way, you could call that boiling, vaporization, and if you're going from steam to liquid, you could call that liquefaction. You could also call it condensation. Going from a steam back to a liquid. But I write all these to realize wordings of questions can have these any of this type of wording. But scientists have settled on what they say this point is, we center on vaporization. And down here, we use the word fusion. So notice that liquefaction shows up twice here. You can go from liquefaction, yeah. If you go from down here to up here, you can use the word liquefaction. And if you go from up here to down here, you can also use the word liquefaction. So I think that's why scientists use the reference of going from water away from water for each one of them. So we say fusion down here and we say vaporization up here. But realize the vaporization point is exactly the same thing as the boiling. It's 100 degrees no matter how you say it. But we just tend to say vaporization point for 100 degrees C and fusion point for 0 degrees C. With me so far? So just to clear up some of the wording, we stick to vaporization and fusion for those special temperatures where a substance changes. And this is just for water, of course. If we were doing ethanol or something else, the temperatures would be different. The temperature at which, what we call a fusion point for ethanol will be different than 0 degrees C. And the vaporization point will be different for ethanol. So I'm sticking with water as a general example here. Okay, so what is specific heat? Where am I going with this? So in 7.10, it gives you this general definition of specific heat. But so specific heat in this chart, we'll kind of stick to calories. I think most of the time this book sticks to calories, but there's also joules. So you have calories, gram degree C, joules per gram per degree C. This is just saying that if you had a sample of solid aluminum, it would take 0.214 calories for every, if you want to take 1 gram of aluminum and change it by 1 degree C, it will take 0.214 calories to change the temperature. So this is clearly stated here. The amount of energy it takes to change 1 gram of that substance 1 degree C. That's what's listed in here. And you need to be told these, you don't have to memorize them. Do notice, here's the definition of specific heat. How much heat does it take to change some mass out of some change in temperature? And this is just showing you the units. But I want to point here, I have to scroll down a little. This is just I'll give you this on a test to help you answer questions. And you probably have to reference this to answer some of the questions from the book. Here we have water is a liquid, water is a gas, water is a solid, AKA water, steam, and ice. And notice that it is different. To change the temperature of steam, it only takes 0.481 calories per gram per degree C. This is actually the definition of a calorie. So the calorie is based on water as well, the same as the Celsius scale. So that's why it's just 1.00 and it's really infinite zeros because that's the definition of calorie. You take 1 gram of water, you raise it 1 degree C, you measure how much energy you put in, and however much energy that is, that's the definition of a calorie. The medical world tends to use the calorie, and the sciencey world tends to use joules, like physicists and higher level chemistry. So what do you do with this? All right, yeah, let me do this. Because there's another concept. There's specific heat. And that involves no phase change. And then there's heat of fusion that you deal with right here. And then the other one is, oh no, fusion is down here. Heat of vaporization is dealt with here. Heat of fusion is dealt with here. All right, so those are the three things, but let me just say that these are specific heats. That's these, there's no phase change. What this is saying is, let me write these up here. 0.481. I'm doing these for water. 481 and 486. Is for the solid. This is for the gas, and this one is liquid. So here's the point. If I've got ice at some lower temperature down here, below its freezing point, it's ice. If I want to know energy it takes to get from whatever negative value that is up to 0, I would say there's a delta T, a change in temperature. To calculate that, I don't mean to calculate the delta T, I mean to calculate the energy. I'm going to use specific heat of ice to get that change in temperature. Meaning I'm going to need this. This is water as a solid, 0.486. So I have to use the specific heat of ice. This is the specific heat of ice. This is a list of specific heats. This is specifically for solid water. All right. If I want to take that same sample and figure out how much heat it takes to go from 0 to 100 degrees, that has another delta T associated with it. To calculate that energy, I'm going to have to use this specific heat water in liquid. This is water as a solid. And then if I want to continue to heat it to something above 100 degrees, in order to calculate that change in energy, I'm going to have to use the specific heat of steam. That is, water is a gas, 4.81. So there will be a delta T there, a change in temperature, and to calculate the energy, we'll use steam. That is water as a gas. You with me? So if you want to calculate how much heat does it take, whatever phase the water is in, whether it's a solid phase, a liquid phase, or a gas phase, you use whichever one of these. You with me? And I'll go through these calculations. But here's the thing. In order to take it from, I'll say, it actually changes from a solid to a liquid at 0. In fact, you're putting heat in to make it go from a solid to a liquid, but that heat that you're putting in is not going towards raising the temperature, it's going towards the melting. Here's your solid, here's a couple of molecules in the solid. They're down here and they're really cold, so they're only vibrating a little bit. You heat them up, you heat them up, you heat them up, you heat them up. As you're heating them up, they vibrate more and more. And then when you get to 0 degrees C, that's the point where they kind of break away from each other and they start swimming around each other. That's melting. You with me? So the vibrations are increasing as you go up, up, up. And then here, the energy you're putting in is actually breaking them apart. And now they're still moving, but now they actually have some real movement associated with them. So the heat you're putting in is breaking those associations that make it frozen. So the temperature doesn't change even though you're adding heat and adding heat and adding heat. But once that very last bit goes from solid to liquid, and you're still putting heat in, now the heat has gone into heating the water, speeding up how fast they're swimming around. So what you need here is you need something called the heat of fusion to calculate how much heat that is. Whatever sample you have, however many grams you have of it, you can calculate how much heat it will take to melt it. So it goes from ice at 0 degrees C to liquid water at 0 degrees C through this transition. It takes a certain amount of heat per amount of gram. So there's a different property. These have specific heats. We also have the heats of fusion for water. And then, again, same idea here. Again, I pointed out that there's a delta T with these. With these there's no delta T. So here, if you go from a liquid to a gas, for this you use heat of a certain amount of heat it takes to take water from a liquid form to a gas form. So 3 different things you need to calculate along this temperature scale. So I'll show you the calculations, but if you see that conceptually, then the rest is just calculations. Let me find some. Okay, how many calories is needed? This is sample problem 7.15. If you've got 1,600 grams of water and you take it from 25 degrees to 100 degrees, all right, we can calculate that, but just gonna erase this. I'll try working over here. So 25 degrees to 100 degrees is going to be something about here. But I need to show you, it's a simple side calculation, but you always have to do that with these types of questions. The delta T is always T final minus T initial. So if you look here, it says from 25 degrees to 100 degrees. The from is the initial, and the 100 is the final. The 2 is the final. Final is 100. Initial is 25 degrees C. So here our delta T is 75 degrees C. So we needed our delta T to continue. So I need that, my delta T. Right. This says, and this is important, how many calories are needed to heat a pot of 1,600 grams of water from 25 to 100 degrees. So what's important here is it goes from 25 to 100 degrees, but they're saying before it boils. You take it from 0 to 100, how much does that take? They're not talking about continuing to go through this point onto steam. But the calculation is, and this really means, I typically like to write this 1 gram to 1 degree C, and we usually put a dot there. So that's this, 1 calorie, 1 calorie is 1 gram, 1 degree C. And then I'm gonna put up here 1,600 grams. They don't have a what do you call it? They don't have a period there, decimal point. So that's 2 significant figures. And then our delta T, and that'll do it. The grams will cancel, the degrees C will cancel, will end up in calories. That's how you would calculate it. You can find out how many calories it would take to heat that water up from 25 degrees C to 100 degrees C. Times 75. So I get that's actually what my calculator says. So that's fine the way it is. No decimal point. That leaves us 2 significant figures, so that's fine the way it is. So 120,000 calories, and you might, that might be the way it's listed if you were looking at a quiz or a test. It might be in kilocalories. You might even see this. No decimal point, so it's still expressing 2 significant figures, but then when I put it in scientific notation, standard scientific notation, I make sure to knock that 0 off. But that's how you do the calculation. All right. Okay, now we're doing iron. If it doesn't say that it changes phases, you're going to assume that it won't. Maybe your intuition tells you 19 degrees C and 150 degrees C. We're nowhere near the melting temperature of something like iron. So we would have to look up here, get the specific heat of iron. 0.107, it says, says do calories and joules. So for iron, space here. me write these down. Iron, 0.107. Calorie, gram, degree C. And for joules, it's 0.448. Now I can calculate these. Okay, practice problem 7.15. You're from 19 to 150. So my delta T what is that? 150. Is that right? 131. Who can do math in their head quickly in the morning? That's not right?
No, I
No,
can't
you can't
do
do the
quick
math.
math.
I don't trust myself, so I'm gonna get my calculator. 131. So that's our delta T. So how many calories did it take to do this? Well, 107 calories, 1 gram to 1 degree C. My delta T is 131 in the grams, 28.0 grams. That'll tell you how many calories. What is it in joules? That'll tell you how many joules. You might be given an initial and final temperature, that is a delta T, and given a number of grams, and told how many calories it took, and then you're actually calculating this, you'll see the variations. So I haven't done a phase change yet. That's separated in another section here, so. Converting a solid to a liquid. Okay, how much energy and calories is absorbed when 50 grams of ice cubes melt? And they tell us here, you need to be told this, you don't have to memorize it, it's 79.7 calories per gram. So that's heat of fusion for, I'm just gonna say water. So the way you would calculate this is 50 grams. Oh, notice this is calorie per gram per degree C. This is calories per gram because there's no temperature change. So these, the heat of fusion and the heat of vaporization are energy per gram. There's no delta T involved. So the calculation is pretty simple. For 1 gram, and then I need the grams, 50.0. That'll do it. 79.7 calories per gram. I think they're gonna stay in calories for the fusions. And you would do the same thing if you were at 100 degrees. Notice, what does it say here? Okay. You're assuming though, they don't say explicitly, that the ice cubes are at 0 degrees C, and the heat that's going into them is only melting them, it's not changing the temperature. So that no temperature change occurred. If it were me writing this question, I would have said, the ice cubes are at 0 degrees C. You can have ice cubes colder than 0 degrees C. And then in order to melt them, you'd have to calculate the energy it takes to get from whatever lower temperature up to 0. That would be a separate calculation, and you would use the specific heat of ice to calculate it. And then you would calculate changing from ice to water. Two separate calculations, and you just add the energy together. That's the total energy it took to melt ice that started somewhere down here to 0 degrees as water. And then the next one is just going liquid to gas. It's the exact same thing. How much heat and calories is absorbed when 22 grams of 2-propanol evaporates? Same thing as boiling. I could have written that as another one of these various words that you can use for this transition. I called it boiling, but I could have called it that just as well. Could have called it evaporating. 159 calories per gram is the heat of vaporization of 2-propanol. So problem 7.18. Notice they tell you the heat of vaporization of 2-propanol is 159. Again, no delta T is involved. 159 calories per gram. And how many grams? 22.0. That'll do it. Grams will cancel. That'll tell you how much energy it took to evaporate, to boil, to vaporize 2-propanol from a liquid to a gas. And again, it's not stated explicitly, but implied that it was at 100 degrees, or it was at its boiling point, whatever temperature that is, it doesn't mention it. And then once it turns to vapor, it's still at that same temperature, that same boiling point temperature. I don't think I'll ask anything on these cooling curves or heating curves on the test, but I'll just point out that they have, just emphasizing that the temperature doesn't change. So they've got temperature on this axis and the amount of heat being added on this axis. We're down here, whatever this substance is, it's a solid here. This is its melting point on the temperature scale, this is its boiling point. But if you're way down here, you're adding heat. If you wanted to calculate that heat, you would use the specific heat. And then this flat part is just telling me that, yeah, we're still adding heat. We go from here on this scale to here on this scale. We're adding heat, but the temperature isn't changing. The process of melting is occurring. See what I'm saying? You're adding heat, melting is occurring rather than speeding up the molecules. And then once it all completely melts, you would use the heat of fusion if you wanted to calculate this amount of heat. And now we would use the specific heat of the liquid form. Once it all finishes melting, and you keep adding heat, you keep moving along this way, now you're raising the temperature. And then when it gets to the boiling point, all this energy that's being put in is going into turning it from liquid to vapor. And then once it's all become vapor, right at that point, that heat that you're adding starts making the temperature go up again. So just to emphasize that the temperature doesn't change during those melting and boiling processes. So I was just going to jump down to intermolecular forces, liquids and solids, specific heat. Let's go to this. So 7.87. How much energy and calories is needed to melt 45 grams of ice? So this time they're explicitly saying it. 45 grams of ice at 0 degrees C and then warm it to 55 degrees C. So what they're saying is, we're ice at, and then we have to melt it, and then we have to go from 0 to 55 degrees C as a liquid. So for this temperature change, we're going to use 1 calorie per gram per degrees C. And then we're going to use the heat of fusion of water to calculate the melting process. So it looks like this. So 0.9. And the heat of vaporization. Okay, so they're giving us these stats up here. But 45 grams of ice, okay, it's 45 grams. And then here, we're going to need the grams, and we're going to need the delta T. 0 to 55 is 55. That is delta T equals T final minus T initial. T final here is 55, T initial is 0, so we get 55 for our delta T. Okay. To calculate it out, it took calculator says 3586.5. 3 significant figures, 2 significant figures, so we're going to keep those. So 3,600 calories. And then the other one, here my calculator says 2475. But 2 significant figures, 2 significant figures. So we're keeping those, we round the 4. And now we just add them together. Oops. 6,100 calories. What I get for that process. Follow that? Okay, I did make another homework. So that one's all about water. So these all just deal with water. Water is the one that I would probably mention that on a test, but you need to know the melting points and the boiling points of any individual substance, so you have to be told that as well. But with water, it's easy, it's 0 and 100. But any other substance, you're gonna have to be told. Right. How much energy, how much energy? look for one more variation of this. Surprised. Okay. This variation on these calculations, that is, I guess this is sample problem 7.16. All right. This is the same type of calculation, what you're being given is different, and what you're calculating is a little bit different. So in this problem, you're being told it takes 400 calories added to 25 grams, 5.0. This is 2-propanol. It's at 21 degrees C. Notice we're being given T initial. And we're being asked, what is the final temperature? So what we have to calculate here is the delta T, and then we can use the known delta T and the known temperature initial to find the final temperature. So you would start by, it gives us the, we need the propanol, 21 degrees C. We're assuming there's no phase change. Propanol. 2-propanol is 0.2612. So we're going to need that. So here's how you would do this. You're given calories, and we're looking for a temperature, so calories needs to cancel out. So use that as your clue. That this is going to need to be flipped over, so the calories will cancel away. So I would start this calculation. I'm going to put this on the bottom, 1 gram, 1 degree C, and 25 grams. That'll do it. And again, notice what we're really calculating here is the delta T. So the calories cancel, the grams cancel, will be in degrees C. What will we get here? 400 divided by 0.612 divided by 25. And my calculator says 26.143979. 3 significant figures, 3, 3, so I'm keeping those. That's our delta T, 26.1. And just to run it out to the end, we've got our delta T now. T initial is 21 degrees C. So we add 21 to both sides. So 26 plus 21. This has 1, this is addition subtraction rule. This has 1 after the decimal, this has nothing after the decimal. So our answer, we have to leave with nothing after the decimal. Adds up to that, but I'm just gonna report it as. Notice again, it says, what is the final temperature? That's what we were actually being asked for. So we found the delta T doing this, and they told us the initial temperature, so we were able to find it. You get this? Okay, so, 2 sections that we went over, 7.10 and 7.12. Specific heat and also heats of fusions and heats of vaporization. And of course I have might not have opened it yet. Physical changes. These are physical changes rather than chemical changes, because notice I never put a reaction up here. When I talk about water, it stayed water. It didn't come apart and become something new. That's a chemical change. Anytime I wrote a reaction up here and something became something different, that's a chemical change. These are physical changes, because bonds aren't broken, new bonds aren't formed. So you distinguish that as a physical change rather than a chemical change. All right. I think that's it for chapter 7. Next, I'm going to skip up in chapter 8 and talk about concentration, specifically molarity. But we will cover some more from chapter 8. I will try to squeeze in just a little bit of basics on acids and bases, because we're going to run out of time. But just so you're aware, it's essentially 8.3 to 8.7 we'll go through. 8.3 and 8.7. And I'll pick out of those what's the most important stuff. But for now, let's go ahead and talk about concentration, specifically molarity. There's a couple of things I sort of glazed over in one of these past chapters. So just for some nomenclature and a little bit of conceptual stuff. So generally, we would call this mixture. And we haven't talked about anything other than sort of pure substances so far. But in chemistry, we're almost always working with a liquid, and that liquid almost always has something dissolved in it, and that's how we deal with it in the lab. And you would naturally call that a mixture. So if I had a beaker that's got, say, some water in it, and I sprinkle some kind of ionic compound in there, if you watch it, or let's say I just sprinkle whatever in there, and you're looking at it, and you see that little bits of solid land in the water, and then they float down to the bottom, and they just sit on the bottom still solid. That's not a mixture. The way you would say it is, that solid does not dissolve in that liquid, so you don't have a mixture there. I think most books start playing word games like it's a heterogeneous mixture, because it's not heterogeneous. But really what we usually mean is, consider a different case where you sprinkle some stuff in the water and it hits the water and it starts to, you watch it and the water's a little cloudy, but then it clears up and then you don't see anything. You would say it dissolved in there and you actually can't see it once it dissolves in there. But in any case, solvent, usually a liquid, pretty much always a liquid for chemists. And the solute can either be a solid or a liquid. So, say I have a big beaker of water, and I sprinkle just a little bit of something that dissolves in there. That little bit of stuff that I sprinkled is the solute, and the water is the solvent. So I could do this, I could go, for example, a big beaker of water being my solvent, and I add in there a little bit of NaCl that dissolves into the water. The water is my solvent, and the solute is NaCl. They're a mixture. Once you put those together, we call them a solution. So a solution is a mixture. Usually it's a mixture of a liquid and a solid that's now dissolved in it. But sometimes it's another liquid. You can mix two liquids too. So that's just a little bit of nomenclature, a little bit of concept. But now what we're talking about is how much did you put? How much solute did you put in the solvent? So let's say we have a beaker, and then we'll just assume it's got some water in it. And then I drop my NaCl in there. And actually it's Na ions and Cl ions. Really it's a bunch of Na plus and Cl minus floating around separate from each other. Those do make an ionic compound, but when I say it dissolves, you drop it in there and you have a bunch of Na plus floating around in here, a bunch of Cl. You could do this. You could take your beaker of pure water and then go over to the scale and measure out, let's say you measured 1.63 grams of NaCl on the scale, and then you dumped all of that into the water. And you looked at your water, the scale of you wouldn't do this with a beaker, but let's say you measured it with a cylinder earlier, and you know that you have 1.63 grams of NaCl in, let's say, 223 milliliters of H2O. You could then say, so what I'm expressing here is a concentration. It's an amount over an amount. It's an amount over an amount. That in general is concentration. There's all kinds of different units we could use though. Here we have an amount expressed in grams and another amount expressed in volume. Expressed as mass, expressed as volume. And we could calculate that out and go, so here's the concentration of this solution I just made up. The calculator says but of course it's 3 significant figures, 3. So I would keep these 3, so 0.00731. And my units are grams per milliliter. And by some context, you would know that the grams are the solute and the milliliters is the solvent, or the milliliters is really the solution. I should say solution here. Because within that volume now, these ions exist in there too, so it's the volume of the solution after you put the solute in there. So this is a concentration. Concentration of this solution I'm talking about is 0.00731 grams per milliliter. That's a concentration. All right. You can do concentrations in several different ways, but chemists almost always do this as the amount of solute in moles, and then specifically liters, not milliliters, not cups, not deciliters. We always do it in liters. So this is a very specific concentration that chemists tend to use. It is a concentration, it's just a very specific one that we call molarity. You with me? I can see the sadness in your faces when I bring up moles again. But it's because moles tends to be a nebulous concept that when we get to molarity, you're already cringing. What else to say before I do some calculations? It's always moles. Okay. So it's still an amount over an amount of solute over an amount of solution. It's just we do the amount of solute in moles and the amount of solvent in liters. What is the molarity of this stuff prepared from 108 grams of glucose and it's 2.0 liters of solution? All right, what you need for glucose here, yeah, they give it to you. I would give this to you. You could calculate if it was something simple like NaCl, the grams per mole. But whenever moles come up, just realize you're going to be probably dealing with grams per mole. But they give it to us. They tell us that this glucose is 180.2 grams per mole. So you're going to need 180.2. You're going to need that. They're asking us for a molarity. They're telling us it's 108 grams and 2.0 liters of solution. All right, so we would do this. Grams. Okay, now we're going to use the grams per mole like this, so the grams cancel. So 1 mole of glucose is 180.2 grams. All right, now we have moles. Now we're going to put the liters down here. That'll tell you the molarity. So the molarity of that solution, 108 divided by 180.2 divided by 2. My calculator says of course it's 3, 4, and 2. So I'm keeping those, so essentially it's going to be this answer. Grams cancel, and we're left in moles per liter, which is what we were after. Because it's a concentration. I can write it like that, or I can say that 0.30 moles in 1 liter. But chemists have invented this stupid thing that I can't believe we have. We don't need that. M literally means grams. But I usually just write this. But if you see this written somewhere in a problem, go ahead and turn it into this to help you start dealing with it. That M just makes it even more nebulous, what molarity is.
Is 180 given to the second part of the problem?
Say again?
Is 180.2 like given to us?
Yeah, you would have to be given that. If it were me, I would have put this up here in the question. But the way they like to go through steps, they just brought it up here.
So on the test, would you give us like the formulas that we
Yes.
need to use?
I mean, I would give you this.
Yeah.
Is that what you meant?
Yeah.
I'll give you the needed information. But realize you can calculate grams per mole, you don't have to do it. They didn't show us the structure of glucose, but if they showed you the whole structure, you could calculate the grams per mole. Okay, so other problems. See this one, calculate the molarity of each aqueous solution, given the amount of NaCl. Aqueous solution means in water. It tells you that the solvent here is water. The solvent is almost always water, because water is cheap and abundant. If you're not putting anything dangerous in it, then it can just go straight down the sink. So we use water when we can. We use other solvents when we have to. Those are done just like these. And notice they give you 58.44 grams per mole for NaCl, but you could have calculated that yourself without any trouble. I'm looking for some kind of variation. Okay, here we go. What volume in milliliters of a 0.3 molar solution of glucose contains 0.025 moles of glucose? And they're actually using the thing we just calculated, 0.30. But this problem says, so let me erase everything and start over. Here, the information they're giving us is we have a 0.30 m solution of glucose. And what I'm telling you is as soon as you see this, go ahead and do this on your paper. Moles per liter. That's literally what the M means. Go ahead and translate. And then, of course, you're going to use this like that in your math equation. So go ahead and just get that M out of your way. Go ahead and get that written. It'll help alleviate some of the confusion. So we're given that, and we're also told 0.025. Let's say glue for glucose. So 0.30 m glucose. I should have over here. Solution. And so then you just do this. Moles of glucose. Now we're going to use this, but moles needs to be on bottom, so 0.30 moles of glucose. 1 liter of the solution. It asks for it in milliliters. This conversion is common in these types of problems, but you want liters on bottom. So 1 liter of solution is 1,000 milliliters. And that'll put you in milliliters of solution, which is what you've been asked for. It says those are exact. It's metric to metric, so those are exact. We've got 2 significant figures there and 2 there, so it's just the 83. So molarity. One other variation would be involving grams, and let me see if they ask. This one's just like that one. Alright. This one, problem 8.12, how many moles of NaCl? So here we're being asked for moles, and they're telling us we have 710 milliliters of solution. That solution is 0.15 molar, which is 0.15 m, which is 0.15 moles per liter. So I just turned the m into the moles per liter. Moles of NaCl. So now, this has liters and this has milliliters, so I've got to do the conversion. 1,000 milliliters of solution is 1 liter of solution. It's asking us for moles. Yeah, this is right. So now I'm going to use this 0.15 moles over 1 liter. That'll tell you how many moles. That's what my calculator says. Moles of NaCl. 2 significant figures, no, that's 2 significant figures. So I'm keeping that 0.11. That's how you calculate. So you can be given moles and the volume of the solution and calculate molarity. You might be given grams of the solute, and then you have to translate that into moles, and you put that over the volume. So variations on this type of question. And when I made that quiz yesterday for the makeup points, some of those questions are exactly like the ones in the practice questions. But I looked through it, and there were just some wordings to fix and mistakes to fix. I rely on y'all to go do those, and if there's a problem, you'll let me know. So I hope that hadn't been messing y'all up. But if you're doing these problems and you can't solve one, you should ask me about it. Or if you think you've done it right and the answers aren't right, you should let me know. Let me look at this real quick before I let you go. All right, so for this one, you'll have to calculate. See, it says grams of KCl. As soon as it says grams, you know you're going to need the grams per mole. So, and you can calculate it for KCl. I'll probably just give you those on a test. But I think y'all can do these. All right, good. You guys good? Any questions? Anybody want to meet?